Yeah, until now we had seen the different types of DC generators. We just started on DC motors in the last class. So, in DC motor mainly what we had discussed was separately excited DC motor. But in separately excited DC motor, although we said magnet or the electromagnet will be separately excited, so we may show it somewhat like this. This is my armature and this is the field, and field is being separately excited. So, this is IF, whereas this is going to be IA, which is flowing from my armature supply. Shunt is almost similar. So, shunt will behave almost the same way, and I can say permanent magnet DC motor is also almost similar, except that it will have no possibility of changing the excitation, no possibility of changing the flux. That is the major difference. Otherwise, all of them behave almost similarly. What I am trying to say is separately excited DC motor, shunt motor as well as permanent magnet DC motor, all three of them behave very similarly. We also talked about the torque speed equation. If you may recall, we said that if we are applying VA here, this is the back EMF and inherent resistance is RA. So, I can write EB plus IA RA equal to VA. So, I should be able to write EB equal to VA minus IA RA. So, I can say K phi omega equal to VA minus IA RA. But we also said TE equal to K phi IA. So, I can write this equation now as omega equal to VA divided by K phi minus TE multiplied by RA divided by K phi whole square. So, this we have substituted here basically. So, torque speed relationship is basically a linear relationship which I can plot somewhat like this. If this is the torque speed plane, on one side I am showing omega, on the other side I am showing TE. So, if I try to plot, this will be a straight line characteristics. If I had the armature resistance to be 0, so this would have been the ideal characteristics for the motor. But because I have an armature resistance, there is going to be some drop in the voltage which will also cause a drop in the speed. So, if I may call this point as VA by K phi, which is corresponding to the torque equal to 0 point. So, VA by K phi I can call as the no load speed, that is the speed when torque is 0. But as I have more and more current drawn or the torque demanded from the load side, I am going to have at this point so much of drop in the speed. So, this is the drop in the speed. So, if I say that this is TE1, I am going to have TE1 corresponding to this, the drop in the speed will be TE1 divided by K phi whole square multiplied by RA as per the equation what we wrote. So, according to the equation what we wrote for the speed, I can say VA by K phi minus TE divided by K phi whole square multiplied by RA. So, I have totally 3 variables that I can change, either VA I can change or phi I can change or RA I can change. So, these are the 3 ways of speed control in a DC motor. So, the first method is RA control. The second method is VA control, and the third method is flux control. So, these are the 3 methods of DC motor speed control. So, In armature resistance control, that is RA control, right, we are going to include a resistance in series with the armature. Maybe the field is also connected here, it does not matter. Maybe it is a shunt excited machine and I am connecting VA here. So, this is plus. So, I am going to have a overall current which is the line current flowing here, part of it goes as field current, rest of it goes as the armature current. So, if I try to plot the speed torque characteristics, this is omega, this is TE. So, I am going to have maybe the natural characteristics somewhat like this. If the machine had been ideal, I would have had the characteristics somewhat like this. Now, I am trying to increase more and more resistance. So, this is RA internal, this is RA external. So, if I include more and more resistance, more and more drop would take place. So, I am going to have this as RA external increasing. This is RA equal to 0. This is RA equal to 0. RA external is 0. So, I am going to have actually, once RA external is 0, this is the natural characteristics of the machine. This is the natural characteristics of the machine. But if I try to include more and more RA, I am going to have more and more drop in the armature circuit resistance here, because of which the speed is falling more and more. So, dynamically if I try to analyze this, let us say I am demanding a particular value of torque. Okay. Maybe I was under this operating condition P. So, natural operating point at TE1 is P. So, this is TE1. So, this is the operating point P. This is the operating point P, right. So, now if I actually increase the resistance, if RA external is increased, now what is going to happen is, immediately I am going to see that the current that is flowing here IA will get decreased, because I have VA minus EB divided by RA plus RA external is going to be IA nu. So, IA nu will be less than the original value of armature current. Because it is now less than the original value of armature current, what is going to happen now is, the torque that is produced is going to be proportional to IA nu. So, I am going to have less value of TE produced. So, if I look at actually the speed is going to be TE minus TL equal to J d omega by dt. If you may recall, this is the mechanical equation we wrote, right. Originally TE and TL were balancing each other. So, omega was actually at a steady operating point. Now, TE has decreased. Because TE has decreased, I am going to have clearly the amount of speed that is actually offered, I am going to have d omega by dt being negative. If this is negative, speed will come down. So, if speed comes down, then I am going to have back EMF also will come down. Because back EMF comes down, from this equation I can say IA will increase. So, IA increases and reaches its original value. So, you may see a small transient reduction in the speed, and that will essentially make the armature current increase, and ultimately it will settle down at a speed which is less than the original speed. So, you are going to see that it will be able to offer the same torque. So, in general I can say RA control will always result in speeds less than rated speed. You can never go above the rated speed, provided I am keeping VA at rated value and flux is also at rated value. Both are at rated value. So much so for RA control. The next one what we are going to look at is VA control. So, in armature voltage control, what I am looking at is actually I am going to have basically the voltage is normally applied, which is the rated voltage. So, let me call probably this as rated voltage. So, the speed I am going to get is VA rated divided by K phi, and this is TE, right. If I have VA itself changed without changing anything else further, this is going to be the operating characteristics. So, I am going to have this as VA decreasing direction. So, maybe this is at VA rated, this is at VA1, this is at VA2, this is VA3. So, I will have VA rated greater than VA1, greater than VA2, greater than VA3, and so on. So, as I decrease the voltage, if I try to look at a particular operating point, maybe this is TE1 at which the machine is operating. If I had applied 220 volts, maybe I would have gotten the operating point as P. If I apply say 200 volts, I am going to get the operating point as Q. If I apply say 190 volts, maybe I am going to get the operating point as R, and so on. So, we get lower and lower speed. You can see that the speed is originally probably 1400 RPM, maybe this is at 1200 RPM, and so on. So, I am going to have less and less speed. So, what happens dynamically when I reduce the voltage? When I actually am operating at 220 volts, let us say the speed was, we said 1400 RPM, right. So, we are going to have 1400 RPM when we were working at 220 volts. Now, I am reducing it to 200 volts. When I reduce the voltage to 200 volts, VA minus EB divided by RA is going to be the current. So, originally the current was IA. Now, I am going to have IA reduced because VA has reduced. Now, because of this, torque reduces. So, TE minus TL, which is J d omega by dt. So, omega will decrease. Because omega decreases, I will have essentially EB decreases. So, IA will be restored to its original value, right. So, whenever I change VA, whenever VA is reduced, I am going to have essentially speed decreases. So, VA control is also used only for below rated speed operation. Now, If I am talking about below rated speed and IA restoring to its original value, torque capability remains the same. That means speed will change from 0 to rated value when voltage changes from 0 to V rated. But IA can remain as a constant, no problem. But what we are talking about very clearly is in steady state, not during transient. During transient it will definitely vary. So, in steady state you can have IA as a constant. So, torque capability is a constant. So much so for armature voltage control. But please remember, if it is a shunt machine, we want to keep the flux as a constant, right? We want to keep flux as a constant, then that means the field system has to be supplied separately. Field system has to be having a constant voltage. It cannot have the same voltage which you have given as reduced voltage to the armature system. It has to be a constant voltage. If you do not give a constant voltage, flux cannot be a constant. So, I would say whenever you are varying only one of the values, maybe VA you are changing, right? At that point you have to have flux as a constant and RA also is a constant. We do not want to vary everything, then it will be very confusing. We do not want to vary all the three things at a time. If VA is changing, then we want to keep flux and RA as constants. Right. Now, let us try to look at the last type of control, which is field flux control. So, we are looking at field flux changing, which means I am going to have here the armature. I am going to keep very clearly VA as a constant, because I told you only one thing is changed at a time. Here is my field system. I will put an external resistance and I would vary that. So, this is R external F. This is original RF. So, this is going to be IF and this is I line and this is IA. So, what I am going to keep is basically VA equal to constant, RA is also constant, flux is reduced. Please understand, the inherent resistance what I have is RF. That RF is very much there. I can't include a negative resistance. I can only include a positive resistance. So, increasing by increasing the field circuit resistance, we are reducing the field flux. So, whenever I am going to have field flux reduced, you think about it, omega is equal to VA divided by K phi minus TE divided by K phi whole square multiplied by RA, right. So, you are going to have, even for a constant value of VA, the no load speed is also changed. So, for RA control, or armature resistance control, no load speed did not change, no load speed was a constant, right, it did not change. So, we could see that it was starting from the same point when we drew the characteristics, but here when we draw the characteristics, if I say this is omega and this is Te, maybe the original torque speed characteristics was like this. So, this is the natural torque speed characteristics. Now, if I try to vary the flux, I am going to have probably one of them somewhat like this, the next one some of like this, the next one may be like this, and so on. So, are you getting my point? So, we are having variation in the no load speed itself, and even the rate at which the speed is decreasing, that is also changing. So, they are not parallel to each other. So, we will not have the characteristics also, the characteristics will not be parallel to each other. So, I would say if I have to show the characteristics, basically I should show it as though this is omega, this is the torque, and the natural characteristics are somewhat like this. Now, for some other reduction in the field, I am going to have somewhat like this, another reduction in the field, I may have another characteristics like this, and so on. So, I will have basically the characteristics somewhat like this for the field flux control. And if I look at it, this is field flux decreasing direction. So, if I decrease it, I am going to get more and more speed. So, very clearly field flux control is used for above rated speed operation. So, distinctly please analyze the dynamics on your own and then come to a reasoning as to why you will have initially some oscillations before it settles down to a speed which is higher than the original speed. When we reduce field flux, we can say Te is proportional to flux into Ia. So, I can say even if Ia is kept at rated value, because flux decreases, I am going to have reduction in Te. So, please note there is reduction in Te plus but increase in speed. So, product of Te and omega remains as a constant. So, we call this as Te multiplied by omega, which is power, which is a constant. So, we call this region as constant power region. So, I can say there are distinctly two regions of operation of a DC motor. One is constant torque zone. In this case, we are going to have Va increasing from 0 to rated value, but I will have Ra and flux, both are constants, right. So, I am going to maintain constant torque capability of the machine under this condition. The second region is constant power zone. In this case, I am going to have actually VA frozen at rated value. It is not good to increase VA beyond rated value because the insulations are designed for a particular value of voltage. So, you can't really expect the voltage to be risen beyond whatever is the rated value. Still it is not, it will not remain safe for the machine. Machine insulation will get ruptured. So, we will freeze VA at rated value, RA remains at its inherent value, but flux is decreased. So, we are talking about only VA variation and we are talking about flux variation. RA control is very lossy. So, this is not commonly used. This is used only when you want to demonstrate that RA control can work well for lower speeds of operation. That is about it. So, I would say that although we, for the sake of completeness, we discussed RA control is really not a very recommended one because it is lossy. So, let me draw the speed variation in a separately excited or shunt motor drive. Maybe this is my rated speed, maybe this is 2 times omega rated. So, if I actually look at the flux is going to remain as a constant until omega rated, but after that I may reduce the flux. The flux may get decreased. So, this is flux as well as torque capability, right. So, multiple variables we are drawing. If I look at the voltage will rise like this because as the speed rises I am going to increase the voltage. So, this is VA. Along with this I can plot power also. So, the power will also rise slowly because it is torque multiplied by omega. Now, the power will almost remain as a constant here. The voltage will also remain as a constant, but this will be the reduction in flux and torque. Both are specified with the help of this. So, I would say this region is constant torque region and this region is constant power region, right. So, at this point the flux is decreased. So, armature reaction will show stronger effects. So, you may see that the torque actually decreases more than what we anticipate it to decrease, because armature reaction is going to decrease the flux further and further as it is. Let us say this is 100% flux, maybe some 0.5 Weber. At this point it will be 0.25 Weber. So, very clearly compared to 0.5 Weber, maybe armature reaction was having a reduction of 0.1 Weber, it would have become 0.4 Weber here, but here it will become 0.15. So, 0.15 becomes extremely small, because of which it may not be able to develop enough torque at the end of this, right. So, let us try to see what we do, corresponding to the constant power and constant torque zone. So, constant torque zone will be employed, or constant torque kind of drive will be employed in certain applications like elevator, where maybe so many people get in and I can't ask them to get out. If I want to adjust the speed, I have to make sure that the torque capability is a constant. Hoist, electric vehicles, these are extremely important in terms of constant torque zone, whereas I am going to have in constant power zone. If I try to look at constant power zone, for example, some of the pumps, fans and so on, they do not require such a large value of torque. The torque requirement is low. So, I might like to go for constant power kind of drive. So, here field control may be used, whereas here armature control will be used. So, VA control is used in this case, whereas I am going to have armature control, field control used in this case, right. So, these are the major two things as far as the armature control and field control are there. We have a few more topics to be discussed in the DC motor drive. So, we have not looked at what are all the topics pending. We have still not looked at series motor. I will start on that today. The second one that we need to look at is compound motor, how the characteristics are. So, series motor, actually we will have to do the speed control also. Speed control aspects also we will have to discuss. Then the third one that we need to discuss is starting of a DC motor drive, and the fourth one we might have to discuss is braking. In fact, commutator still we have not discussed, the commutator action also we need to discuss. So, we will just try to take a look quickly at the series motor. Series motor, as I told you, the field is going to be in series. So, I am going to have the armature here and the field is in series, and I am going to apply a supply here. So, if I write this as I line, the same thing is true with respect to IA, the same thing is also IF. So, I will have I line equal to IA equal to IF. Series motor, the major advantage is you will have extremely high speeds possible. So, they are actually used in an application specifically which is at home, mixer and drilling machines. Both use generally series motor, which work at about 15,000 to 20,000 RPM. But please note, at home what we have is AC supply, there is no DC supply. So, when a motor, series motor can work on both AC as well as DC supply, in both if it can work, then we call that as universal motor. When we started the topic of DC machine itself, we said normally field is not laminated in a DC motor, in a DC machine, but in a universal motor we need to necessarily, right, field has to be laminated, because you are applying AC, the flux will be alternating. because the flux is alternating, we definitely need to make sure that the field is also, the field system also has to be laminated. So, the major difference between AC series motor and DC series motor, the difference is the field being laminated. So, field will be laminated in AC, whereas that is not laminated in DC series motor. So, if I look at the series motor, the same equations will be valid. VA minus IARA equal to K phi omega or EB, from which I should be able to derive the speed torque relationship for this. So, already the time is up. So, we will probably continue with this in the next class.